I borrowed these notes from a colleague because I think it does a really nice job of separating out the steps involved in coming up with the products of a double replacement reaction and then figuring out which, if any, of the products would form a precipitate. So that's what we're going to start with today. We're going to look at the 4 ions that would be present in the solution given the reactants in a double replacement reaction. We will recognize that the positive ions will switch partners to form the 2 new products, so we'll come up with those 2 new products. Then we will check the product formulas to make sure that the new compounds formed are neutral, essentially balancing the oxidation numbers in the new compounds. And then we're going to use table F, which is not a very fun table to use, but we're going to use table F in order to find if there is a precipitate that is an insoluble product or something that would not dissolve in water. So the first step, we're going to find the ions present in the solution. So in this first compound that we have, when it dissolves in water, it's going to break apart into 2 different ions. Since we can see 3 different elements in this compound, IC3, look at table E, you will know that you have a polyatomic ion. So we're going to use table E to identify which 2 of these elements form the polyatomic ion. Unless you can already see it, then you wouldn't necessarily need table E. I'm going to pull it in now, and now we can use it in order to find that polyatomic ion. We only have these 3 positive polyatomic ions. The first part of this compound is none of those. So we know that the NO3 is going to be the polyatomic ion. So we're going to search through and find it because it'll be very helpful to also have its oxidation number. It is negative and they imply a 1. So we're going to have Ag as our positive ion, NO3 minus 1 as our negative ion. We didn't assign the positive ion its oxidation number yet because we need something else to figure that out too. So let me pull in the periodic table so we can find that. So here is silver, and silver only has 1 positive oxidation number, it's +1. If it had more than 1 positive oxidation number, we would have to figure out what that positive oxidation number is based on what NO3 is. Now we have our other compound, K with Cl. Here's K and Cl. And we're going to, again, for these ones, just look in the periodic table. Here's K. It is a +1. Here is Cl over here. It does have multiple oxidation numbers, but the only negative is -1. And it has to be negative. It's the last part of our compound. The first part is positive. The last part is negative. All right, let's do that again for the next one. We have Cu is the positive part, Cl is the negative. We've already looked up Cl, we know that's -1, but we have a little issue when we look up copper, Cu. It can be either +1 or +2, so we have to figure out what it is. In order to figure it out, we're going to look back at the formula. Chlorine is -1. Multiply that by the subscript for a total of -2. The whole compound needs to total 0, so copper must total +2. And since there's only 1 atom of copper, its oxidation number is going to be +2. So we can transfer that over here. And then for our other ion, again, IC3, look at table E. So our first part here would start with Mg, but there's no Mg as one of our positives. So it must be the CrO4 that's together, and you find that right here. It's called chromate. The Mg would be the positive. When we looked up chromate over here, it was 2- or -2. You can write it either way. That's on the whole thing. And then magnesium right here is +2. We'll do another together. I see 3. Look at table E. Again, Na isn't one of the positives, so the OH must be the negative. So we'll put Na here, OH here. And now we got to figure out their oxidation numbers. Na is going to be +1. And then OH, you know, will have to be -1, but here it is, just to confirm. -1. The other reactant, NiSO4, Ni is not one of the positives, so it must be, by that I mean Ni is not one of the positive polyatomic ions, so it must just be here. And then SO4 must be the negative polyatomic ion, which is right here. It's -2. And now we look up nickel. Here's nickel. It can be positive. Here is nickel. It can be +2 or +3. So based on what sulfate is, all of sulfate here is -2. There's only one of them, so nickel must be +2. I want you to try the next few, and you're welcome to use the tables we have right here. Go ahead and pause this. I'll move this up so you can see that and the examples, and go ahead and try those and then compare it to mine. All right, so here's all the answers now, and I want to point out some of the issues I typically see when I see this. Because this subscript is referring to everything within this parentheses, this subscript is actually due to the oxidation number on sulfur. So you're not going to write this subscript down when you write down your polyatomic ion. When you write down a polyatomic ion, the only parts of that formula you should record are things that you see in table E. Don't bring this 2 with it. Same thing with this NO3. Don't bring that 2 with it. That 2 is there because of copper's oxidation number. And that's the other thing I wanted to talk about with this example. Copper has more than one oxidation number possible. So in order to figure out what it is, you need to figure it out based on nitrate. Nitrate, when you looked it up in table E, was -1, and there's 2 of them for a total of -2. So copper would have to be +2, and when you divide that among the atoms of copper, since there's only the 1, it would be +2. That's where I got this +2. Sodium is a +1, phosphate -3, calcium +2. OH, note I did not bring this subscript. It's outside the parentheses. It's referring to how many hydroxides I would need because of calcium's +2. Lead, again, is one that has more than one positive oxidation number, but since acetate is -1 and there's 2 of them, lead must be +2. Iron's another one like that. You do it based on iodine. Since there's 3 of those, iron must be +3. So that's where these numbers came from, that +3 and that +2. Lithium's +1. Carbonate's -2. I did not bring the 2 from the lithium over here. We're not going to necessarily need that 2 when we make our new products. Sulfate's -2, barium +2, chlorine -1. Nickel is +2 based on sulfate. Sulfate, polyatomic ion, is -2, so nickel must be +2. That's a plus. So let's look down at our next chart, because we're going to use the ions we came up with to come up with our products. In order to come up with our products, if you recall, the positives are going to switch, or you can look at it as the negatives are going to switch. Some of my students have found some success in kind of equating it to the FOIL method in math. The difference being that we're not going to do the first and the last. We're going to do the inside and outside, or however you want to look at it. We're only doing 2. So this silver is now going to be paired with that chlorine, and then this potassium is going to be paired with the nitrate. Really important when you write your formulas, the metal comes first in the formula. It doesn't matter if you do the silver and chlorine together first or the potassium and the nitrate first. The order of the products don't matter, but the metal within your product formula needs to come first. So let's say we do silver with the chlorine first. Again, write down those oxidation numbers. If they do not cancel out, look for a common factor. If there isn't one of those either, swap and drop. Now our other product is going to be the potassium with the nitrate. Keep in mind that the potassium must come first and then the nitrate. And you know, I like to put parentheses. Now we assign our oxidation numbers. They cancel out. You don't need to do anything more. In fact, if you like to, you can erase those oxidation numbers. I'm not going to bother now. In fact, for this one, you didn't even really need this parentheses. The last thing we're going to do here is identify if we have any precipitates. This is using Table F, and Table F is not easy to use. So let's take a moment and talk about Table F. So here is Table F, and the reason why it's not easy to use is there's really two tables within this one table. This first half of our giant table is talking about soluble ions. So all of these ions that are listed here are typically soluble, or they dissolve in water. So if you put them in water, they would eventually dissolve like salt or sugar does. The exceptions to that is that sometimes with halides, so that would be anything containing chlorine or bromine or iodine, if that formula for your halide includes silver, lead, or mercury, it is an exception to the idea that halides are typically soluble. So what that's telling us is that if you have silver iodide or lead bromide or mercury chloride, those are not going to dissolve. They will be precipitates. So that's how you use that half of the table. The other half of the table includes ions that are typically insoluble, meaning that they do form precipitates most of the time. They include carbonates, chromates, phosphates, sulfides, and hydroxides. But just like anything else, there's always exceptions to it. In fact, most of these exceptions are the ones here that have no exceptions. So they're always soluble. Carbonates are typically insoluble, but they are soluble if they are combined with a group 1. So if you have sodium carbonate, sodium is a group 1, it will dissolve. If you have lithium carbonate, it will dissolve. If you have ammonium carbonate, it will dissolve, and so on. Essentially, and this is what I usually ask my students to do, if you shade in these two middle columns, so the exceptions to the first column and the insoluble compounds here, if you shade those in, those are the ones that form precipitates. So the reason I have you shade it in is to make it look cloudy, like your solution would be cloudy. You would have a precipitate there. It would come out of solution. Another trick I give my students is that not all of the positive ions that you could come up with are in this table. So whenever you look up a compound to see if it's soluble or not, look it up based on the negative half of the compound. Those are mostly listed. A lot of times the positive half of the compound is an exception, or it's listed as group 1, so it's kind of hard to actually see what you're looking for. So look it up based on the negative half of the compound. So let's go ahead. I'm going to shrink this a little bit so we have a little more room to look at these. Let's see if we can find either of these in this table. We have, because we're going to look this up based on the negative half of the compound, we have a chloride. So we're going to start over here at the top of that first column and see if we can find chlorine in this. Oh, there's chlorate, close. Oh, here's chloride right here. Chlorides are typically soluble, but there are exceptions to that. So if chlorine ended up combined with silver, lead, or mercury, it would be an exception to being soluble. Or if you've shaded this in like I asked you to, you would know that this is a precipitate. So we actually have a precipitate in this reaction, AgCl. I have never heard of a reaction where you end up with two precipitates, but I also don't claim to be an expert on much of anything except being me. So I like to look up both of them just to confirm. Plus, if you find you have two, then maybe you've made a mistake. So we're going to look up the other one as well, again, based on the negative half of our compound. So we're looking for nitrate. Oh, here it is right here. Nitrate is in that soluble column. There are no exceptions, so it is definitely soluble. Let me tuck that away for a second while we come up with our next two products. We're going to take our copper, and it's now going to be with chromate, and Mg is going to be with Cl. This time, just to prove that it doesn't matter which product you put first, I'm going to do the Mg, which is a +2, with the Cl first. Oh, those don't cancel out, so I swap and drop. And then my copper, which we said was a +2, with chromate, and I like to put those in parentheses, was a -2, and those oxidation numbers actually cancel out. So I don't technically need these parentheses, but I like to have them. So we've come up with our two products. Now we need to check and see if any of them are precipitates. So we're going to start with the MgCl2, again looking it up based on the negative half of the compound, the Cl2. So I'm looking for chlorine. We found this once before. They are typically soluble. And we're going to check and see, is magnesium an exception to that? It is not. So the MgCl2 is soluble. Let's check the copper chromate. We're going to look it up based on the chromate. Nothing in that first column. We skip the exceptions, go to the next column. There's chromate. Chromates are usually insoluble. So this is likely insoluble, but let's check and see. Does copper make this an exception? It says that group 1s are an exception. Well, that's not a group 1. It's not lithium or any of those. Calcium, magnesium, those are group 2s, or ammonium. Nope, doesn't mention the transition metal copper, so we can assume that that is going to precipitate, CuCrO4. Okay, let me tuck table F away again, and let's see if we can come up with the products in our next reaction. We have sodium now with sulfate, nickel with hydroxide. So as I said before, it doesn't matter which compound you create first. This time I'm going to go with the sodium compound. We're going to have Na with SO4. Notice I put it in parentheses. I like to do that. And then I'm going to assign the oxidation numbers that we figured out from before. They don't cancel out. They don't have a common factor. So when I swap and drop, the 2 is actually going to become a subscript on Na. My other compound, nickel, was a +2. And then hydroxide, -1. They don't cancel out. Here's where it's really important that you had those parentheses, because now when we swap and drop, that 2 needs to be outside the parentheses. All right, now we're going to check table F, see if either of those is a precipitate. So we have, again, looking it up based on the negative, the sulfate. Oh, sulfates are usually soluble, but we're going to check sodium, see if it's an exception, and it is not. So the sodium sulfate will be soluble. Let's try the nickel hydroxide. Again, looking it up based on the negative half, the hydroxide. Oh, here it is. It's usually insoluble. And let's make sure nickel is not an exception. Nickel is not a group 1, it's a transition. It's not calcium, barium, strontium, or ammonium. So that means that NiOH2 would be a precipitate. Let's do another one together. I'm going to put this back in the corner, move things up a little bit. Our next one, again, looking at the ions we came up with at the top, we have ammonium now with nitrate, copper with sulfur, so NH4, again I'm going to put my parentheses with nitrate, NO3. See, the ammonia was +1, nitrate was -1. They cancel out. So if you don't have those parentheses, you would still be entirely correct. Now our other compound is going to be the copper, which we said was +2, with the sulfur, which was -2. They cancel out, no subscripts. Now we check in table F for a precipitate. Again, we're going to look it up based on the negative half of the compound. There's nitrate. It's soluble without exception. So this will not precipitate. So we're looking for sulfides. Here's the sulfides. They are typically insoluble. We're just going to check to see when it's combined with copper if it makes it an exception. Nope, not group 1 or ammonium. We do have a precipitate, and it's copper sulfide. What I'd like to do now is send you off to have you try the next few. You'll be able to check your answers against mine when you're done. So here's the rest of the answers. What I did when I created all the formulas was I only used parentheses when they were absolutely necessary. So those of you that are trying to figure out when you have to and when you don't have to, I only put them in when you absolutely have to. So it made sodium hydroxide, calcium phosphate, note the subscripts, and the calcium phosphate was a precipitate. The next one we made lead iodide, notice the subscript, and iron acetate, again, notice the subscript. The lead iodide precipitated. The next one we made lithium sulfate, again needing a subscript on the lithium, and magnesium carbonate. The magnesium carbonate would be a precipitate. Carbonates typically are, and the magnesium was not an exception. The last one we made barium sulfate. Notice no additional subscripts. You do need this 4 because the sulfate has that. And then nickel 2 chloride with the 2 on the chlorine. And then sulfates are typically soluble, but the barium made it an exception. So we have this as being a precipitate.